Welcome back to the deep dive. Today we're tackling something huge, uncertainty itself, and specifically the mathematician who kind of gave it its modern rules, Andrey Kolmogorov.
Yeah, Kolmogorov, active from the 1920s right through to the 80s. He's the guy who took randomness, which often felt like just a shrug, and turned it into a proper, rigorous language. So our mission today is to really get into how he did that. We're talking probability, complexity, even the chaos of turbulent fluids, how his work basically built the infrastructure for understanding so much around us.
It really is amazing. His whole project, you could say, was about making these huge, messy concepts rigorous. Probability needed solid rules. Turbulence needed a universal description. And randomness, well, he wanted to make it something you could actually measure, something operational.
Operational randomness. I like that.
Building a kind of grammar, yeah. One that can handle perfect order and total chaos.
Okay, so let's start right at the foundation. You mentioned making probability rigorous. Before him, in the early 20th century, it was a bit loose, wasn't it, compared to other math fields? It was, yeah. Useful, definitely, but lacking that axiomatic foundation. So Kolmogorov's big move around 1933 was to say, okay, let's define probability using measure theory, which is a really powerful branch of analysis.
Measure theory. Sounds intimidating.
It can be. But the core idea is actually quite neat. He defined a probability space with just three things, usually written like omega fp in brackets.
Right, okay, but break that down. If I'm just rolling a standard die.
Perfect example. So omega is just all the possible outcomes for a die that's 1, 2, 3, 4, 5, 6. Simple enough.
Got it. The sample space.
Exactly. Then F, script F usually, that's the collection of events we might care about. Things like rolling an even number, which is a set 2, 4, 6, or rolling a 5. It's basically all the questions you're allowed to ask about the outcomes.
Okay, so the outcomes and the questions about the outcomes. What's P?
P is the probability measure itself. It's the function that assigns a number between 0 and 1 to each of those events in F. So P rolling an even number, 12, P rolling a 5 equals 16.
So he wasn't inventing probability, but giving it this airtight set of rules, like the absolute bedrock logic for chance.
That's a great way to put it. And the consequences were huge. Random variables weren't vague concepts anymore. They became proper mathematical functions, measurable functions. And expectation, the average outcome, became an integral.
An integral, like calculus.
Yep. Suddenly you could use all the powerful tools of calculus and analysis to prove things about probability, like limit theorems, in a really clean way, to solidify the whole field.
Okay, that's the structure for known possibilities. But you mentioned randomness itself. This is where my head starts to spin a bit. How do you define true randomness? Like, not just unpredictable, but fundamentally patternless.
Yes. This leads us to one of his other huge ideas, algorithmic randomness and Kolmogorov complexity, usually written Kx.
Okay, lay it out. Kx.
So Kx is defined as the length, specifically the length of the shortest possible computer program running on some standard universal computer that can produce the string x and then halt.
Shortest program. Okay, so if my string x is, say, 1,000,000 A's in a row.
Right. The program might be something like print A 1,000 times. That program is very short compared to the 1,000,000-character string itself. So that string has low Kolmogorov complexity. It's compressible. It has a pattern.
Makes sense. So high complexity means...
High complexity means the string is essentially incompressible. A string x is considered algorithmically random if its Kolmogorov complexity, kx, is roughly the same as the length of the string itself. There's basically no shorter way to describe it than just writing out the string.
Wow. So randomness is incompressibility.
That's the core idea. It's the ultimate definition of something having no hidden pattern or structure.
I remember reading something tricky here, that you can't actually calculate kx for any given string. Is that right?
That's the kicker, yes.
Yes.
It's mathematically proven that kx is uncomputable. You can find programs that produce the string, so you can find upper bounds on kx. But you can never be absolutely certain you found the shortest possible program.
So we can never definitively label a real-world sequence like digits of pi or noise from a distant star as truly algorithmically random.
Strictly speaking, no. We can have very strong evidence, like if it resists all known compression algorithms really well. But we can't have mathematical proof in the absolute sense. It remains a kind of theoretical ideal. And this ties into how, say, motion theory views it. MT would argue that what we perceive as randomness in the physical world is always relative to us, the observers, with our limited tools and measurement precision.
Ah, interesting. So MT connects this abstract math back to physical limits.
Exactly. For MT, probability PA isn't just an abstract number. It's about the proportion of physically possible ways the system can move micropaths that end up resulting in event A. The law of large numbers happens because certain patterns of motion, certain synchronizations, are just more stable and likely over time.
That feels much more grounded. Okay, so if randomness is incompressibility, what about the rate at which systems become random or unpredictable? Like a chaotic system, how fast does it lose its memory of where it started?
Right, that's about the dynamics. And for that, we look at something called Kolmogorov Sinai entropy, or KS entropy,
Hmm.
often written HKS. This came out of his work with Yakov Sinai on dynamical systems.
Chaos entropy. How does that work intuitively?
Imagine you have a chaotic system, like weather patterns. You start two simulations with almost identical initial conditions, maybe one tiny difference in temperature somewhere. If the chaos entropy is positive, those two simulations will diverge exponentially fast.
Exponentially, wow.
Yeah, it quantifies how quickly the system generates information, or you could say how quickly it becomes unpredictable. Each step forward makes the future state exponentially harder to pin down based on the initial state.
So a high chaos entropy means rapid chaos.
Very rapid chaos. And
Okay.
again, MT offers a physical interpretation here. It sees chaos entropy as the rate of desynchronization. It's how fast the different moving parts of the system lose their phase relationship with each other, how quickly they decouple.
So zero chaos entropy would mean stable, predictable motion.
Exactly. It means the system is either locked in a periodic cycle or maybe quasi-periodic, but nearby states aren't flying apart exponentially. There's coherence.
Coherence versus desynchronization. I like that framing. Now, quickly, before we get to fluids, you mentioned stochastic processes and a 0-1 law. That sounds very binary.
It is, and it's deeply weird. Kolmogorov's 0-1 law deals with tail events in processes that unfold randomly over time. A tail event is something whose outcome depends only on the infinitely far future behavior of the process, not any finite starting part.
Okay, like what?
Like, will a random walk on a number line eventually return to zero infinitely often? That depends on the whole infinite path. The 0-1 law says the probability of any such tail event must be exactly 0 or exactly 1. It can't be, say, 12.
Wait, so it's either guaranteed to happen or guaranteed not to happen given infinite time, no middle ground.
No middle ground for those specific kinds of long-term events under the right mathematical conditions. It's counterintuitive because we think of randomness as preserving uncertainty, but this law shows some long-run outcomes become certainties. It really forces you to think about limits.
Okay, mind slightly blown. Let's shift gears now to something more tangible, maybe turbulence. That classic image of chaotic fluid flow, smoke swirling, river rapids. Kolmogorov tackled this head-on too, right? With his K41 theory.
He did. K41 from 1941 was revolutionary. It was an attempt to find universal statistical laws governing fully developed turbulence, arguably the most complex classical physics problem.
So what was the big idea? How did he approach that mess?
He proposed the concept of an energy cascade. Imagine energy being put into the fluid at large scales, like stirring a big tank, creating large eddies or swirls.
Okay, big swirls.
Because viscosity isn't very effective at these large scales, these big eddies are unstable. They break down into smaller eddies, and those smaller eddies break down into even smaller ones, and so on.
Like a chain reaction.
Exactly. Energy cascades down from large scales to smaller and smaller scales. This continues until the eddies get so tiny that viscosity does become dominant, and it dissipates the energy as heat. Friction takes over.
That makes intuitive sense. A cascade of energy. How did he make it quantitative, though?
He focused on the inertial range. That's the middle ground of scales, small enough that they've forgotten the details of the large-scale forcing, but large enough that viscosity hasn't kicked in yet. Energy is being passed down.
Okay.
In this range, he predicted a universal scaling law for the energy spectrum, EK. EK basically tells you how much energy is in eddies of size roughly 1K. And he showed, based on dimensional arguments and assumptions of isotropy and stationarity, that EK should scale like k to the power of minus 53.
The famous minus 53 law. Why is that specific number so important?
Because K41 claimed it was universal. It shouldn't matter if it's water, air, or plasma. In the inertial range of fully developed isotropic turbulence, you should see that K53 energy spectrum. It suggested a deep underlying statistical structure common to all turbulent flows. A huge claim.
And he gave experimentalists something concrete to measure too, right? The 45 law?
Yes, the 45 law is incredibly important. Unlike the 53 law, which relies on some assumptions about how the cascade works, the 45 law can be derived more directly from the fundamental Navier-Stokes equations governing fluid flow, assuming isotropy and stationarity.
So it's more fundamental.
In a way, yes.
Hmm.
It relates the third-order velocity structure function, basically a measure of how skewed the velocity differences are, directly to the energy dissipation rate, epsilon. Because this exact relation, S3R equals only to 45, epsilon R. It became a crucial benchmark for testing if experimental or simulated turbulence really fits the K41 picture.
But K41 wasn't the final word, was it? People noticed problems when they looked closely at real turbulence, this idea of intermittency.
Exactly. K41 assumes this nice, smooth, self-similar cascade. But real turbulence is bursty. You get these localized regions and moments of extremely intense activity, sharp velocity gradients, high dissipation. It's not uniform. That's intermittency.
So the real world is lumpier than the theory predicted.
Precisely. K41 kind of averages over these bursts. So later, Kolmogorov himself and Obukov proposed refinements, often called K62, that tried to account for this intermittency, often by assuming the energy dissipation rate itself fluctuates, maybe following a log normal distribution. And this is where MT comes back in, offering its interpretation. MT views the cascade fundamentally as a transfer of coherence. Intermittency, in this view, is what happens when the local synchronization density of the flow breaks down dramatically. You get these local hotspots of desynchronization, leading to those intense bursts K41 missed.
Okay, let's really focus on that motion theory perspective now. We've seen Kolmogorov's incredible mathematical structures for probability, for entropy, for turbulence. How does MT take that framework and, well, add a layer of physical mechanism to it?
That's the goal. Kolmogorov provided the essential grammar, the rules for how the numbers should behave. MT tries to explain the physical story producing those numbers. It adds the why of motion to Kolmogorov's what of statistical structure.
So, probability axioms. Kolmogorov defined omega, F, P. How does MT see that?
Like we touched on, MT sees PA, the probability of event A, as emerging from the physical possibilities. It's the proportion of allowed ways the system can move, the viable micropaths or synchronization patterns that lead to outcome A. The law of large numbers isn't just math. It's the system settling into its most stable, physically robust synchronization patterns over time.
So, probability becomes a direct outcome of physical constraints and stability.
Yes. It's driven by coupling strengths and how things can synchronize or fail to synchronize.
And for turbulence, Kolmogorov's energy cascade becomes
A coherence cascade. Large eddies represent large regions of relatively synchronized motion. As they break down, this coherence is transferred, but also partially lost, to smaller scales. Desynchronization increases as you go down the cascade. So turbulence isn't just about energy flow. It's about the rate at which coherence or synchronization leaks out of the system.
And this framing helps explain intermittency.
MT suggests it does. K41 implicitly assumed a uniform rate of coherence loss, leading to universal scaling. But MT expects that if the synchronization density varies spatially, some parts of the flow are more tightly coupled or coherent than others, then you'll get non-universal behavior. You'll see deviations from the simple scaling, which look like intermittency.
So MT predicts where K41 might break down based on the local coherence of the flow.
That's the idea. It uses Kolmogorov's structure, but points to physical synchronization variations as the reason for things like intermittency, suggesting it might not be entirely random bursts, but tied to the underlying coherence field.
It feels like it's trying to make the statistics less abstract and more tied to measurable physical properties of the flow itself.
Exactly. It respects the math Kolmogorov built, but tries to ground the statistical parameters, like epsilon or structure functions, in the physics of synchronization and desynchronization rates.
Which brings us to today. How does this framework, Kolmogorov's math plus MT's physical interpretation, lead to new, actual experiments or tests we could run?
Well, the most direct tests would aim to manipulate the physical coherence and see if it affects the supposedly universal statistical laws, like the 45 law.
How would you do that?
MT proposes, for instance, designing specific wind tunnel experiments. You'd try to actively disrupt the coherence of the flow at certain scales, maybe by introducing controlled fluctuations or obstacles that force desynchronization.
Okay, so you actively mess with the flow's synchrony.
Right. And the prediction is that doing so should directly impact the measured value of that supposedly constant factor in the 45 law, or at least narrow the range of scales over which the law holds. You'd be testing if that universal number is actually sensitive to the physical coherence you're manipulating.
Tying the abstract math directly to a knob you can turn in the lab, that's powerful.
It's about moving from statistical description to causal mechanism.
Looking back, Kolmogorov's achievement was just immense, wasn't it? Giving us this language to talk precisely about uncertainty, from coin flips all the way to atmospheric chaos. He really did find a kind of rhythm inside the roar.
He absolutely did. And it's fascinating, too, that his work spans both extremes. We focused on chaos and randomness, but his early involvement with CAM-AM theory, Kolmogorov-Arnold-Moser theory, actually showed the opposite in some cases.
Ah, right. Can-M theory is about stability, isn't it?
Exactly. It shows that some orderly, quasi-periodic motions in dynamical systems can actually survive small perturbations. They don't all instantly descend into chaos. So his legacy covers both the breakdown of structure and its surprising resilience.
Resilience versus breakdown. That's a great way to frame it. And maybe that leaves a final thought for you, the listener. When you look at the complex, messy systems in your own life or work, think through that Kolmogorov lens. Ask yourself, how fast is the desynchronization happening here? What's the real rate of information loss? And maybe, just maybe, is there a shorter description hiding in all that noise?